Imagine you're inspecting this massive modern suspension bridge. You expect the blueprints to be mathematically perfect from day one. Right? Like every cable, every beam is calculated for optimal load distribution.
Right. You expect pure engineering.
Exactly.
Mm.
But then you look closer at the actual structure, and you notice this massive load-bearing pillar that it seems entirely out of place. And you find out it was added purely because the engineers, well, they ran out of the original high-tensile steel halfway through construction, and they had a deadline.
So they compromise. And now the entire integrity of the bridge, the way all the traffic flows across it, depends on that one slightly awkward decision made, a decade ago.
Yeah, it becomes a structural anomaly that permanently defines the foundation. You can't just remove it without collapsing the entire thing, so you build around it.
Which is exactly what happens in software architecture all the time.
Right. And before we get too deep into the blueprints today, I want to clearly state for you listening that this is an AI-generated deep dive. We were pulling from 2 decades of authoritative C++ committee design documents, developer postmortems, and architectural teardowns by language designers like Herb Sutter.
We're looking at a very specific anomaly today in the realm of systems programming. We are tracing the historical evolution of futures and promises design in modern C++.
Yeah, and the timeline stretches from the heavily fragmented pre-C++11 era all the way to the highly anticipated structured concurrency models of C++26.
Which brings us to our core mission for this deep dive. We want to answer a very specific question for professional systems engineers. Why does the standard future work the way it does, and what architectural constraints define it today?
Because to master modern C++, you can't just memorize syntax.
Exactly. You have to understand the historical constraints, the underlying memory mechanics that really forced the committee's hand.
Okay, so let's unpack this. We aren't just doing a basic tutorial here on like how to call an asynchronous function. We're doing a full architectural autopsy. So take us back to the philosophical foundation. What did the landscape actually look like in the late 90s and early 2000s before C++ had any concept of concurrency?
Well, the landscape was entirely defined by what the C++ 98 and 03 standards called the abstract machine. And this abstract machine was strictly, uncompromisingly single-threaded.
Wait, strictly single-threaded. So the language itself just pretended concurrency didn't exist.
Completely oblivious to it. The compiler had no idea that multiple threads could be executing instructions simultaneously.
Meaning if you were building a high-performance, multi-threaded application back then, and I mean, plenty of people were doing that, you were just completely stepping outside the bounds of the standard language.
You were on your own. You were relying entirely on target-dependent operating system APIs. So UNIX engineers were deeply embedded in POSIX threads, or threads, which is this very low-level C API where you manually manage thread identifiers and utexes.
Oh my God.
And Windows engineers were writing entirely different code, using the Win32 threading API with functions like createThread and objects like critical section.
So writing cross-platform code was just a nightmare of preprocessor directives, basically just trying to keep the application compiling across different machines.
Yeah, but the compilation wasn't even the scariest part. The bigger issue was the compiler optimizations.
Right, because if the compiler doesn't know other threads exist, it's going to make assumptions that completely break concurrent code, isn't it?
That is the truly terrifying part of the pre-concurrency era. A C++ '03 compiler would aggressively optimize your code based on single-threaded logic. It would reorder memory writes to make execution faster.
Or it would cache a shared variable into a CPU register and just read from that register instead of constantly checking main memory.
Exactly. And in a single-threaded program, that's a brilliant performance boost. But in a multi-threaded program, another thread might update that variable in main memory, but your first thread never sees it because it's looking at a stale cache in the register.
Oh, wow. So you just get these catastrophic, silent data races.
Catastrophic. It wasn't until libraries like Boost.thread provided a portable abstraction over these OS-specific APIs that the committee felt heavily pressured to integrate concurrency directly into the C++ standard memory model.
But as they started drafting C++11, they ran into 2 massive architectural hurdles.
Yeah.
The design documents refer to them as the return value gap and the exception gap.
Yeah, so adding a standard thread and standard mutex was actually the relatively straightforward part. Those are really just wrappers around those operating system primitives. The real gap was in passing results back and forth.
Okay, break that down for me.
Think about a standard synchronous function call. The return value is placed neatly on the caller's stack, right? But in an asynchronous call, the function is executing on a completely different stack, potentially on an entirely different CPU core.
Right. They are physically separated in memory, and the exception gap is even worse. I was reading through the notes, and there's this brilliant analogy for the mechanism of an exception in an asynchronous context.
Oh, the warehouse analogy.
Yeah. It's like sending a worker to a warehouse across town to retrieve a specific box for you. If the box isn't there, which represents an exception being thrown, the worker doesn't, like, pick up a radio and call you to report the issue.
Because there's no communication channel back to your thread.
Exactly. So instead of communicating, the worker just locks the warehouse doors and burns the entire building to the ground.
That paints the picture perfectly. Before the standard future was introduced, if a worker thread threw an unhandled exception, it had absolutely no mechanism to jump across thread boundaries back to the parent stack.
So what did the runtime do?
The C++ runtime would just catch the unhandled exception, immediately call standard terminate, and abruptly crash your entire application.
Just instant death for the program. So the committee needed what they called a vocabulary type. They needed a standardized way to represent a value that doesn't exist yet, but will eventually.
Right, and they needed a secure channel to funnel either that value or the exception back to the caller thread, all while strictly adhering to the C++ philosophy of zero overhead abstractions.
So they needed to cleanly decouple the act of producing a value from the act of consuming it. The producer needs a way to fulfill a promise, and the consumer needs a way to wait for that future reality.
Exactly. So let's trace how they actually built this. Looking at the chronology of the early 2000s, the committee was under immense pressure. They were designing what would become C++11, and there was a very real fear of over-engineering the standard into oblivion.
So they had to make some compromises.
Yeah, this period was defined by the Kona Compromise. The Standards Committee met in Kona, Hawaii, and basically agreed that they had to stop endlessly debating theoretical perfection. They needed to prioritize a stable, well-understood set of features to ensure C++11 could actually ship.
Because if they didn't, the language might just lose its relevance. So looking at the early proposals, we're talking about papers N2561 and N2671, authored by engineers like Detlef Fullman, Howard Hinnant, and Anthony Williams. We see the concept of an asynchronous return buffer.
Yes, which was the direct, somewhat clunky ancestor to the standard promise and standard future. And soon after, we see Anthony Williams' paper N2709, which introduced the standard package task.
And that was designed to elegantly wrap any callable object and automatically funnel its result, or catch its exception and push it into a future.
Right. But here is where we hit a massive architectural fork in the road. Because you can't talk about the launch of standard async in C++11 without talking about the most glaring omission in the standard.
I saw this in the documentation, and it completely baffled me. They launched asynchronous programming.
Without standardizing a thread pool.
Yes, without a standard thread pool.
Yeah.
They gave developers a way to launch tasks, but no standardized machinery to efficiently manage the threads executing those tasks.
It remains one of the great historical what-ifs of C++ language design. Several early proposals, specifically N2185 and N2276, explicitly argued that standardizing a thread pool was mandatory.
Because if you call standard async without a thread pool to handle the request, the runtime has to literally ask the operating system to spin up a brand new raw OS thread for every single function call.
Which involves a massive context switch. You're allocating a new stack in kernel space, running this tiny task, and then tearing the whole thread down. The overhead of creating the thread vastly outweighs the actual work you're trying to do.
So why didn't they include one?
Well, the alternative to spinning up threads is running the tasks serially, which completely defeats the purpose of parallel execution. The committee knew this, but standardizing a robust, highly optimized, general-purpose thread pool that performs perfectly across every single operating system architecture, it was deemed far too complex.
They figured it would delay C++11 by years, right?
Exactly. So they deferred it to a technical report that, well, never fully materialized, leaving us with a concurrency standard missing its engine.
Wow. So without that thread pool, the committee had to finalize what became the shared state architecture of C++11. This is where the mechanics get super fascinating. Let's break down how a standard promise and standard future actually talk to each other under the hood. It's not a direct connection, is it?
No, it utilizes an asymmetric handle model. The crucial mechanism here is that Neither the standard promise, which is the producer, nor the standard future, the consumer, actually owns the result.
They just act as handles.
Right. When you create them, the runtime performs a heap allocation to create a shared state object. Both the promise and the future hold a shared pointer referencing this heap allocated middleman.
So this shared state is doing all the heavy lifting of synchronization. It holds the actual value, or a standard exception pointer, to catch our warehouse-burning worker thread. And it holds a state flag indicating if the work is ready and an atomic reference count.
And that atomic reference count is what makes it perfectly safe.
Huh.
The producer can fulfill the promise and immediately destroy its handle, or the consumer can get bored, drop its future, and walk away.
Because the shared state is reference counted, the memory remains totally valid and safe from being prematurely freed until both the producer and consumer are entirely finished with it.
Exactly. To make this usable, they gave us standard async, which came with two distinct launch policies. You had eager execution using launch async, which forces a new thread, and lazy execution using launch deferred, which delays the execution until the consumer explicitly asks for the result.
But to make this shared state mathematically safe from data races, the library working group had to enforce extreme microscopic granularity on the API, didn't they?
They absolutely did. Look at LWG issue 1050, for example. The documentation strictly enforced a one-to-one relationship between a promise and a future. When you call getFuture on a promise object, the runtime only lets you do it exactly once.
Because if multiple consumer threads are holding futures pointing to the exact same shared state, they're going to race to read and write the internal state flags.
Right.
And you get memory tearing.
Precisely. And beyond just object relationships, the committee had to patch fundamental atomic typing rules. In paper N2925, resolving LWG 879, there was a critical issue where the atomic memory address inside the shared state was being const qualified in certain contexts.
Okay, wait. Why does an atomic address being labeled const matter so much to a systems engineer?
Because high-performance systems rely heavily on lock-free data structures. To write a lock-free queue, you don't use mutexes, you use a compare and swap loop or a CAS loop.
Right, where you look at a memory address, compare it to what you expect, and atomically swap it with a new pointer.
Yes. But if the standard suddenly dictates that the pointer you are holding is immutable, if it's const, the compiler outright refuses to let you perform the swap. The committee had to urgently fix that atomic typing rule, or building a lock-free concurrency primitives in C++11 would have been mathematically impossible to compile.
Unbelievable. So the committee meticulously designs this highly synchronized shared state. They plug the exception gap, they establish a vocabulary type, they fix the atomic typing for compare and swap operations. It sounds elegant on paper. So when did the architecture hit the wall?
It hit the wall when this elegant abstraction met the unforgiving reality of object lifetimes. This introduces the first and really the most notorious constraint of C++ futures, the object lifetime conflict.
Okay, how did this surface?
A few years into the design process, compiler engineers like Hans Bohm and Lawrence Krauss published paper N2880. They realized there was a terrifying edge case regarding how threads die.
Let me trace out the mechanism here just to make sure I've got it. Say I'm writing the main thread of an application. I launch a background worker thread, and I detach it. Detaching meaning the worker is now running completely independently, the operating system is managing it, and my main thread isn't waiting for it to finish.
Okay, now what happens if your main parent thread finishes its work and begins its shutdown sequence? It starts destroying its local variables, including thread local storage.
Okay.
But that detached worker thread is still churning away in the background, and suddenly it attempts to access a reference or a pointer to one of those parent variables that was just destroyed.
Oh, that's a textbook dangling reference. The worker thread is going to read corrupt, freed memory, and the entire application is going to segfault and crash violently.
Exactly. To prevent this specific nightmare, the committee was forced to implement a very heavy-handed rule, requirement 30.6.8/5. They mandated that the destructor of the last future referencing a shared state created by standard async must block the calling thread until the asynchronous operation completes.
Wait, let's think about the practical consequence of a blocking destructor. Say I'm writing a simple fire and forget logging task, right? I call standard async to write a file in the background. Standard async hands me back a temporary future object.
Yep.
Because it's fire and forget, I don't even assign that future to a variable. The compiler reaches the end of the statement and immediately destroys the temporary future.
And because it is the last future referencing that shared state,
The destructor blocks my caller, My background logging task is forcing my main thread to wait until the file is written. My asynchronous code just became perfectly painfully synchronous simply by existing.
You have just articulated the exact trap that infuriated the entire C++ community. This single requirement effectively ruined the standard future as a general-purpose composable library type.
Wow.
Herb Sutter actually published a famous architectural teardown in paper N3630 titled Composability Failure. He systematically proved that if an API returns a future, the caller has absolutely no way of knowing if destroying that future will block their thread.
Which is an absolute disaster for anyone writing, say, a graphical user interface. If you're on the main UI thread and you drop a feature and its destructor blocks for even 100 milliseconds waiting for a background network call, your user sees the entire application stutter and freeze.
This composability failure led directly to our second major constraint: ecosystem fragmentation and compiler schisms. The blocking behavior was so catastrophic for UI responsiveness that Microsoft's Visual C++ compiler team looked at the ISO standard and simply refused to implement it.
Wait, really? They just ignored the standard?
They ignored the blocking destructor rule entirely to protect their Windows developers.
But that creates a massive portability trap. I could write a beautiful, non-blocking fire-and-forget system on Windows using Visual Studio. It runs flawlessly. I'd take that exact same code base, port it to a Linux server, and compile it with GCC.
And your server hangs. Because the GCC engineers adhered strictly to the letter of the ISO standard. And GCC's strict adherence caused other compounding issues too. Because there was no standardized thread pool in C++11, GCC often implemented standard async by forcing a heavy OS thread creation for every single call.
Which just decimates CPU performance.
Right. Or, to avoid that overhead, it would silently default to lazy deferred execution.
Meaning developers thought they were writing highly parallel systems, but GCC was secretly executing the tasks synchronously, one after another, only when the result was explicitly requested.
Yes.
So if the blocking destructor was universally recognized as a massive architectural flaw by language designers, why didn't the committee just patch it in C++14 or 17? Paper P3466 tried to fix this, didn't it?
It did, but that introduces the third constraint, which is arguably the most brutal lesson in language design: the backward compatibility trap. P3466 attempted to explicitly break this blocking behavior and free the destructor. The committee rejected it.
Let me guess. Because by the time they realized the depth of the flaw, there were already billions of lines of legacy C++ code out in the wild. And some of those developers were actually relying on that exact blocking behavior as a quick and dirty synchronization barrier.
Exactly. If the committee changes the standard, they silently break the world's infrastructure. It forces C++ into this permanent, additive nature. Flawed features, once standardized, remain in the language forever.
You can't remove the awkward pillar from the bridge. You just have to engineer new, better pillars alongside it.
Precisely.
Which really explains the modern pivot. We spent time dissecting the unstructured, eagerly allocating concurrency of C++11. It's clear that the standard future is essentially a dead end for composing complex, high-performance execution graphs. So how do you actually get around that? I mean, you can't just stop using concurrency.
No, you can't. The industry is completely abandoning the future model for a paradigm called structured concurrency. For a long time, the committee tried to salvage futures. They worked on a concurrency technical specification, paper P0159, which attempted to add a .then method to futures.
Allowing developers to chain tasks together asynchronously without blocking, right? Like how promises are chained in JavaScript or C#.
Conceptually, yes, but mechanically, in a systems language aiming for zero overhead, it was a total disaster. They realized that chaining standard futures still required a massive trail of dynamic heap allocations for the shared states and internal mutexes to protect the state transitions between every single step of the chain.
It fundamentally violated the performance requirements of low-latency systems.
Right. So that specification was ultimately withdrawn. The modern solution, arriving in C++26, is paper P2300, the standard execution library, which is centered entirely on senders, receivers, and schedulers.
Okay, let's build a new analogy to understand this mechanism. A standard future is like ordering food at a busy restaurant. You place your order, that's standard async, and the cashier hands you a plastic pager. That pager is your future. You go sit down, and you just hold it, waiting for it to buzz. Your execution is paused.
That's the eager model, exactly.
But a sender and receiver model feels entirely different. It's more like designing the blueprint for a factory conveyor belt. You place all the raw ingredients in the hoppers, ensure every gear meshes perfectly, and then, and only when the entire pipeline is built, you flip the main power switch.
That is a brilliant way to conceptualize the shift from eager to lazy execution. A sender simply describes the work to be done. It does not start the work. A receiver is the continuation, the callback that handles the output of the sender. And a scheduler dictates the execution context, like an actual standardized thread pool.
Finally. But what is the mechanical benefit of building the entire conveyor belt before turning it on? How does that eliminate the overhead we saw in C++11?
Well, think about what the compiler sees. Because it is strictly lazy, the C++ compiler can see the entire execution graph before a single instruction is executed.
Oh, I see. With futures, the compiler just sees this dynamic web of heap-allocated shared states being passed around at runtime. It can't optimize that.
Exactly. With senders and receivers, the state of the entire operation can be calculated and stored locally on the caller's stack. There is no need for dynamic heap allocations or reference counting because the lifetime of the operation is strictly bound to the scope of the pipeline.
So the compiler can just aggressively inline the asynchronous tasks, completely eliminating the overhead.
Yes.
Tying this back to the hardware level, what does this shift actually mean for a systems engineer listening right now? I mean, the standard future was built for an era where we just wanted to avoid blocking the main thread, and now we're talking about eliminating microscopic heap allocations.
The C++ abstract machine can no longer pretend hardware doesn't exist because we are hitting physical power limits. Look at the data center constraints industry leaders like Jensen Huang and Andy Jassy are warning about. The ultimate bottleneck in cloud computing is no longer floating point operations per second. It is literal gigawatts of electricity.
So every cycle spent allocating memory or stalling a thread is just wasted power.
Exactly. Modern CPUs rely heavily on instruction-level parallelism, or ILP. They try to execute multiple instructions simultaneously within a single core by predicting what comes next.
And the opaque state transitions, the mutex locks, and the dynamic allocations of a standard future actively stall those CPU pipelines. They literally force the processor to wait.
Right, whereas senders, because they are transparently composed at compile time, allow the compiler to reorganize instructions and feed the CPU pipeline flawlessly.
Okay, let's synthesize this architectural deep dive. We just spent 20 minutes dissecting the flaws, the blocking traps, and the performance bottlenecks of C++11 futures. But it sounds like the committee's early decisions weren't necessarily failures so much as stepping stones.
It is a story of necessary iteration. The C++11 standard future achieved something monumental. It established a lingua franca, a common vocabulary.
It finally allowed the industry to move past platform-specific C APIs.
Yeah, and it brought the concept of asynchronous values directly into the language's memory model. It paved the way for everything we are doing now, even if it failed at composability.
So for the practitioners listening, here is the actionable intelligence. First, limit your use of standard async to simple, non-performance critical one-off tasks where a little heap allocation won't hurt.
Yes.
Second, deeply internalize the blocking destructor trap. If you spit up a temporary future and let it drop out of scope, you're accidentally writing synchronous code.
A very common, very deadly mistake.
And third, start mentally migrating your architectural designs toward the lazy, zero-overhead pipeline paradigm of C++ 26 senders and receivers.
You have to adapt to where the compiler intelligence and the hardware constraints are intersecting. Structured concurrency really is the only viable path forward for systems programming.
Which brings me to a final thought for you to mull over as you look at your own code bases.
Yeah.
We've seen how the necessity for zero-overhead execution is forcing developers to abandon manual thread management and instead build these massive declarative execution graphs for the compiler to optimize. It makes you wonder, if compilers are now taking over the complex orchestration of execution pipelines just to save power and maximize instruction parallelism, will the systems engineer of 2030 even be writing logic anymore?
Or will we simply act as directors, defining the constraints for a compiler that writes the actual execution paths for us?